To measure extreme industrial environments, engineers have traditionally relied on electronic sensors, but deploying these sensitive devices near high voltage or heavy electromagnetic interference introduces a severe risk of catastrophic failure. The flaw is inherent to the architecture. Traditional instrumentation relies on the flow of electrons, which makes the sensors themselves highly vulnerable to external magnetic and electrical fields corrupting the signal. The structural solution to this interference is optical fiber. Because the fiber is composed of inert dielectric materials, specifically glass, it is completely immune to ambient electromagnetic interference. While these fibers are globally recognized for facilitating zero-loss data transmission, their unique physical properties offer a secondary, highly specific utility. They can be engineered into sensitive diagnostic tools. An engineer can transform a passive data conduit into an active environmental sensor. Instead of just sending data, the system deliberately measures physical perturbations in the light wave itself. Substituting electron flow with photon propagation detaches the active measurement from electromagnetic vulnerability, allowing us to gather data in previously impossible environments. This block diagram illustrates the foundational components required for any fiber optic sensing system. The architecture begins with an optical source, generating the carrier wave. The initial segment of optical fiber then delivers these photons directly into the sensing environment. The critical juncture is the transducer block. Here, an external physical measurand, like temperature, strain, or pressure, interacts with the system to alter the light. The modulated light travels through the return fiber to a detector and an electronic processing unit, translating the photonic shift back into readable data. While this macro architecture is universal, the specific physical engineering of that central transducer block varies drastically depending on the application. To organize these variations, we classify fiber optic sensors along two primary axes: the transducing approach, which dictates how the light is modulated, and the topology, which dictates where the sensing physically occurs. Navigating this two-axis framework is a strict requirement for architecting a sensor network tailored to a specific harsh environment. The first major categorization on our transducing axis is the extrinsic or indirect approach. In an extrinsic system, the fiber functions strictly as a waveguide, carrying light to a separate external mechanism. Inside this device, the light beam is physically manipulated. Mechanical shutters, chemical reactions, or physical gaps alter the beam in response to the measurand. The primary engineering advantage here is modularity. Because the sensing happens off-fiber, these systems often rely on simpler, intensity-based modulation logic. For example, an engineer might route a fiber into an external optical switch designed to trigger only under specific physical vibration or mechanical closure. Because the optical fiber remains isolated from the target environment, the actual sensing burden in an extrinsic architecture lies entirely on the mechanical ingenuity of that external device. The second categorization is the intrinsic or direct transducing approach. Here, the optical fiber itself operates as the active transducer. External perturbations like physical stress or thermal expansion directly alter the physical geometry and the refractive index of the glass. This shifts the characteristics of the propagating light. This chart illustrates 4 parameters of a light wave modulated by internal physical changes. First is amplitude or intensity modulation. Bending or microstress causes light energy to leak out of the fiber core, decreasing the total returning radiant power. Second is phase modulation. When physical strain alters the optical path length, it induces a measurable phase shift, requiring a sensitive interferometric setup. Third is wavelength modulation, involving a spectral shift of the returning light's frequency, commonly executed using fiber Bragg gratings. Finally, polarization modulation occurs when the electric field's orientation within the wave is twisted by external magnetic fields. We see this applied in advanced systems utilizing the magneto-optic Faraday effect. By wrapping a single-ended optical fiber around a conductor, engineers can measure unidirectional or bidirectional current up to 6,000 amps purely by analyzing the polarized twist of the light. In intrinsic sensors, the transmission and sensing mediums are indistinguishable. The physics of the wave itself serves as the diagnostic tool. Beyond how the light is modulated, we must also classify where the measurement physically occurs in space. This spatial configuration is formally defined as the sensor's topology, and this diagram maps its 3 tiers. The most basic architecture is the single-point sensor. It is restricted to taking a reading at one discrete terminal location at the far end of the line. Monitoring large-scale infrastructure with single-point sensors requires a massive, complex volume of individual cables terminating at exact locations. This logistical constraint necessitates the multipoint or quasi-distributed sensor. This setup multiplexes a finite number of discrete sensing locations along a single continuous fiber path. This drastically reduces wiring complexity compared to traditional electronics, allowing one optical line to service multiple distinct read zones across a facility. The final topological category to explore is the intrinsic distributed sensor. In a distributed architecture, every single millimeter of a multi-kilometer fiber acts continuously as the sensor. By applying a processing technique called optical time domain reflectrometry, or OTDR, engineers map continuous strain or temperature data along this completely unbroken path. Using these topological classifications, engineers can scale a network from a microtarget to continuous structural monitoring across tens of kilometers of pipeline, entirely without localized electronics. By crossing our two axes, the transducing approach and the spatial topology, we create a matrix that dictates real-world deployment. Consider high-voltage transmission equipment. To measure direct current while eliminating arc risks, an engineer deploys an intrinsic single-point architecture utilizing the Faraday effect. Conversely, supplying low-level power and transmitting sensing data within the intense electrical fields of high-powered antenna elements requires an extrinsic point-to-point setup. Meanwhile, structural bridge or pipeline monitoring strictly demands intrinsic distributed sensors to detect microcracks over immense spans. Selecting the wrong quadrant, such as deploying an extrinsic array for distributed pipeline monitoring, guarantees systemic failure or massive logistical bloat. Modern infrastructure frequently operates in severe thermal, chemical, and electromagnetic extremes, where traditional electron-based sensors simply cannot survive. Fiber optic systems bypass these constraints because they shift the mechanism of measurement away from electrical currents and directly onto the physics of light modulation. By mastering the distinct architectures of transduction and topology, engineers gain an analytical precision that scales from a single point of failure to a 50-kilometer length of pipe. Shifting the act of measurement to the modulation of light provides a high-fidelity framework for how we map, monitor, and interact with the physical world.
Thanks for watching and grow every day with just a bit of information. Like and subscribe for more content and learning.